All right, so we're on 6.3 in our textbooks, and what this is all about is proving identities. We talked before about identities. If we go back real quick to some diagrams here, this is a shot from the textbook, right? And we talked about sum identities, difference identities, double angle identities. In the very first section, we talked about the Pythagorean identities and the reciprocal identities. So what we have is we have an arsenal of tools to change a single trigonometric identity into an expression involving the same trig identity or others, right? For example, your sine of 2a, right, is 2 times sine a cos a. So that's a different way of writing the same thing. So what we're talking about now is proving identities, is we're talking about showing how the look of it one way is the same as another look of it, okay? So let's just read here some notes. It says, in order to prove that a math statement is true for all values of the variable, okay? If we stop right there, we can test 1 or 2 or 10 or 100 versions, right, or variables into some kind of statement. And we can test whether the left side is equal to the right side. That's what we did yesterday, right? And so that is not a proof, though, okay? That is not a proof. What we need to do is we need to show algebraically that this works for all possible values of the variable. So as we continue, it says identities that are already known must be substituted into either or both mathematical expressions so that they appear to be exactly the same. So again, the key is we're using identities, okay? So identities are being substituted into this statement to see if they're the truth. And we'll go over lots of examples in a minute. You must manipulate each side separately, okay? So here is an important statement as well. When we're talking about proving something to be equal, we cannot assume the equality. And you may not realize you're doing this, but let's say something like this, 2x plus 5 equals 15, all right? When we solve for x, what we can do, because this is equal, we can subtract 5 from both sides. I can divide both sides by 2 and get x all by itself, right? So that is something that we do when we solve equations, solve for a missing part of an equation. But that's because we assume that the equality is true. In this section of mathematics, we are not assuming that the left side equals the right side, but we are trying to prove that it's true, okay? So an example would be if I have 30 over 2 and I'm trying to prove that that's equal to 15, okay? If I'm trying to prove something oversimplified like this, well, what can you do? You can manipulate this one side, but you can't bring anything over from the other side, okay? Because that is assuming equality. So what I would do is you would say, okay, well, I know that 30 divided by 2 actually simplifies to 15. Okay. So that actually, if I reduce this, or let's say, you know, you're showing these complicated steps, and you say, well, 30 has a factor, okay, or has factors of, just give myself some space here, 30 is actually 2 times 15. And so that 30 can be written as this, and this can be, obviously, is still there. And then you say, because this happens, this side actually equals 15. And then you say, hey, there we go. I've proven it, that they are exactly the same. So this is what we're doing, except with these trig functions. Okay? That's really what we're doing. Notice I didn't bring anything over from here, didn't multiply both sides by something, didn't assume any equality. I just changed the one side so that it looks like the other side. Got that? And that's exactly what we're doing. So this 2 times 15 would be like an identity of 30. That is true all the time. If you have 30, you can rewrite that as 2 times 15. So that's what we're going to do with the trig functions. Okay? Now, what this first part says here, this is a clip from your textbook. Okay? And it says that verifying an identity, okay, this is not proving, but this is verifying. If we verify an identity using specific values, and that's where we would test an angle like we did yesterday, then we can say that yes, this validates the statement that it is true for that value only. Proving an identity has to go further than that. And as I mentioned, it's done algebraically and validates the identity for all permissible values of the variable. So for example, if we pumped in here 60, okay? We just, and again, you don't have to write this down. I'm just showing you. If I put 60 in here, okay, 60, what is the sign of 60, everyone? Help me out here on your calculators. What's the sign of 60? Or maybe you know this from the unit circle. What is it? Root 3 over 2. Okay. So the sign is the second coordinate, and sign of 60 is way up here, right? So that's kind of that 0.866 root 3 over 2. Good. And what is cos of 60? That is 1/2, and the tangent of 60 is root 3. Right. It is root 3. So check it out. This is root 3 over 2 on this side, and this is root 3 over 2 over here. So those are equal. That means that this statement right here is verified when theta is 60. You have an indication that, hey, this might be true all the time, but this is not the proof that we're going for in this section. Okay? That is just for one specific value. So to prove a trigonometric identity algebraically, and if you want to write the stuff down here that you can, this is in your textbook, so it's on the key ideas on that last page of the section, so you don't have to write it down. I am going to kind of move fairly quickly, but as I go over this, I'm going to do an example here. So this says to prove a trig identity algebraically, algebraically, there's a few tips and there's a few methods that I'm going to help you to do this, okay? Because it's going to feel like a daunting task sometimes, but if you have some tips and some guidelines, it's going to make this go a lot smoother, okay? So one of the things that I just kind of mentioned was that we have to separately simplify both sides of the identity into identical expressions, okay? And of course, how we're doing this is we are using identities to substitute. Okay? We're using identities to substitute. And in this last section, okay, I was helping you with some questions there before. That's exactly what we're doing, right? You're taking a look at something and you're saying, hey, can I rewrite that in a different way in order to manipulate this whole side? Okay? So we're using identities to substitute. The second point that's going to go along with this example here is it's usually easier to make the more complicated expression simpler than it is to make a simple expression more complicated. Okay? So you simply have more tools to work with here. Okay? Look at, you have one. One can actually be written in different ways. And you can use identities to rewrite this. Good. Cos of 2x. Oh, there are 3 different ways you could write this. Sine of 2x. There's a different way to write that. So you see how this is more complicated, but we have a lot more options to do some substitution. With tan x, yeah, maybe the options are a little bit more limited, okay? And so this is more to work with here. All right, so if we did this example here, notice I'm not going to put an equal sign here, okay? There is no equal, but I am trying to prove that this side is the same as this side, and we're going to try and get them to look identical. So what I do when I do these, and what I'm encouraging you to do, is to put a little line in between them, so that you remember that you can't, be bringing stuff from one side to the other. Like for example, I cannot multiply both sides by sine 2x. Can't do that. Okay, can't go past the wall. Not going to happen. All right. So you keep everything separate. But what you wouldn't want to notice here is, like I mentioned, there are a few ways that we could rewrite this. Now, we're going to leave the 1 alone, okay? And this is the tricky part. How do you decide what to rewrite? And yes, that is the tricky part. And all I can tell you is that the more that you do, the quicker and easier the right sort of path will pop out to you. But it is going to take practice, okay? If you do 5 of these from now until mid next week when we're done this section, if you only do 5, You're going to have no idea. It's going to be still really complicated. If you do 25, you're going to be a lot better at recognizing what you should do. Okay? So it just comes down to practice. Cos 2x. Okay. Well, actually, let's start with sine of 2x. Let's start with that. We're going to rewrite this. How can I rewrite sine of 2x? There's only one option there that's given in those, right? So what is that? Sine of 2x is the same as 2 sine x times what? Cos x. Okay? You all see that on your identities chart, right? In your text or in your notes, whatever. So you see that? Okay. Now, what we're going to be looking for here is, again, to simplify this whole side. And I have a bit of a problem with this cos 2x. You cannot go, hey, cos 2x and cos x, close enough. Can't do that. Not going to happen. But I'm going to focus on cos 2x. Is there a way that I could rewrite cos of 2x that might give me an option to do some simplification of factors here? So, for example, do we have cos of 2x in terms of sine or cos? Yes, we do. Okay. Again, let's look at our options. If we zip back here, our options are right here. Okay. So which one do you think we could do? Well, probably not this one. Probably not this one, because that's a difference of squares. That's got squared both of these. Let's just focus on eliminating, one of the trig functions, focusing on one of these. Okay? So either one of these. Anybody have an idea of which one you want to try first? Okay, well, let's just try this one. Okay, what do you guys know, right? Don't know anything yet. That's fine. Let's just try one of them. 2 cos squared, hey, it's truth. It's okay, don't feel bad. It's the first time you've ever heard this. 2 cos squared a minus 1. Let's do that one. Oh boy, okay. So let's do 2 cos squared a, and then it was minus 1. Okay. Oh, sorry, that's going to be an x in this one, right? It's a for the kind of general format, but it's x in this question. Okay. Okay. Well, do you see anything that we could do with this one right here? Anything that we could now change or simplify, or any like terms we could combine to... Anybody see anything? You could what? Eliminate? Yes. Okay, very good. Look at this is a positive one. This is a negative one. So if I combined those, I'd get 0. So you could just cross them out if you want. I'm going to just erase them. And this is what I'm left with. Ah, okay. Okay. We're getting close here, aren't we? Now, you may not see this, and this little step you probably don't have to show as you get better at this, but this is what I'm going to do. Cos squared x, please remember, is the same as cos x times cos x. Okay, you remember that? So now you can maybe clearly see, and I'll outline this in yellow now, I have a factor here. I have a factor here. A factor here. And in the denominator, I have a factor here. I have a factor here. And I have a factor here. Okay? All right. Now, all right. So, okay. Man, I'm foreseeing a problem here. In my haste, I think I might have missed something. Can anyone see it? Okay, so once we've got these brackets put in here, okay, we have to change things just a little bit here. And once these brackets are removed, this is actually what we have over here. And we have, now I can take a 2 out, and I have 1 minus cos squared x. Okay, 1 minus, because that 2 is gone, right, out there, over 2 sine x cos x. So like I say, I apologize. I thought this was going to be a little bit easier one for your your first one, but apparently not. But it's going to be okay. Okay, so we get to this point, and hey, maybe when we chose this one substitution for the cos 2x, maybe it would have given us actually a bit of a quicker path. Actually, I didn't know. I just wanted to put a random one in there